In this last video, before the midterm, we will cover 3.1 soundness and 3.2 post theorem, or completeness. So within these two sections, we are going to be able to describe these two main theorems, or rather meta-theorems, and explain their importance. So soundness essentially tells us that our Boolean logic is sound and truthful. What does that mean? It means that everything we can prove using the Boolean logic is actually true. So we don't prove anything that isn't actually true, right? And we discussed this a little bit by saying that when we were building logic, by building our axioms and our rules of inference, that we wanted to verify that they were actually true statements, they were believable. And now we need this soundness theorem to justify why our method of proof, so for example the rules we follow for Hilbert-style proofs, and all of the other meta-theorems to justify the equational-style proof, are sound, right? So that they actually prove things that are true. Whereas post-theorem, or completeness, tells us our Boolean logic is complete. This means that everything that is true and can be represented in Boolean logic can actually be proved using this Boolean logic. So there isn't anything within Boolean logic that we could state that we know is true that we can't prove using Boolean logic. So that tells us that the construction of our Boolean logic is also complete. So this is a theoretical understanding, which is really important and is sort of the foundation for everything that we've been doing. So it's meant to justify why it is that we're going through each of these steps. But we can also use both of these theorems for practical applications. So the first application is of soundness, and we're going to be able to use soundness to disprove fallacy. So we're going to be able to disprove statements like this. So in order to prove A does not prove B, we will be able to use soundness, which will be really helpful because, as you can imagine, to prove something like A does not prove B, essentially we need to consider all possible proofs from A and show that B can never be written in any of those proofs. So that's a very big task that we really do need soundness for. And also within our class, we'll be able to use completeness to show provable equivalences. So we'll look at that more directly in class. Okay, so let's look first at soundness and what it formally says. So the first thing we discussed before was simply that we need to justify why what we built our logic on, so those primary rules of inference and logical axioms, are in fact truthful. So we'll leave it as an exercise for you to show exactly what that means. So we'll talk about what it means, and then we'll leave it as an exercise for you to justify these two things. So recall, our first rule of inference, equanimity, states the following. So if we have A, and if we know that A is equivalent to B, then we can prove B, right, is how we apply equanimity. So to determine whether this rule of inference is truthful, it means that instead of saying if we have A and we have A equivalent to B, then we can prove, or then we have B, instead we say that A and A equivalent to B tautologically implies B. Okay, so I'll leave that for you to check. And the second statement of Leibniz says that if A is equivalent to B, then substituting in any other well-formed formula with A is equivalent to substituting in for B. So instead of that as a proof statement, you need to justify that if A is equivalent to B, so that A equivalent to B tautologically implies that substituting A into C is equivalent to substituting B into C. The other thing that I already asked you to check was that all logical axioms are, in fact, tautologies. So this lays the groundwork for our logic, and this is the connection between proving something and it being true. And finally, soundness is a meta-theorem which tells us that if gamma proves A, then gamma tautologically implies A. So that's what is meant by everything we can prove is in fact true. So being true is exactly how we discussed it in section 1.3. Okay? And the proof of this is again a proof by induction on the length of proof where A occurs, right? So our assumption in proving this is that gamma proves A, so we would assume that there is a gamma proof of A, and we use that fact and induction to show that gamma tautologically implies A. And this proof is given in the textbook and also within the notes posted on Moodle. So to expand your knowledge and particularly your comfort in proof by induction, you can certainly check that out. So this is the general statement. Then of course the corollary says that if A is an absolute theorem, then A is a tautology. So here, assuming that gamma is empty, then we simply get the corollary from that. In the case that gamma is not empty, what this really says that if A is a relative theorem, then it is a tautological implication of its hypothesis, gamma.